Central limit theorem. So again, central limit theorem for any sequence of IID random variables. So for any sequence of IID, again random variables, I have a sequence of random variables IID, okay, with finite mean and variance. So the mean and variance of that should be finite, whatever sample I have, okay, the mu, mean, and the sigma variance, sigma square, they should be finite, okay. So the distribution, though I have collected many samples, so as this sample, there are many samples are there, so as the this end increases, right, so the sample means, the sample, I'll collect my multiple samples. Say for example there are one sample x1, x2, x3, there are multiple samples like this xn, so each sample will have x1, x2, x3, sorry, x3, small x, xn within that, and then x11 like x12, x13 like that, x1n, and this will have x21, x22 like that till x2n. So they all are having n samples, okay, and each one will have, say this is x1 bar, this will give me x2 bar, and similarly this will give me xn bar, okay. So I have these n samples, each one has these many, say n is 100 here. So I have these IID random variables, and within that each sample I have, say n equal to 100, and I am doing this multiple times. So this is one. So I took one sample of 100 people for I am calculating the average height of a city. I took one sample of 100 people, I found the average height. I took another sample of 100 people, I got average height as x2 bar, and similarly I did it n times, okay, and I got, or say for example, I don't confuse, I'll do it k times, okay. This is a n here, so this n and this is different, so this will be xk bar. So this is my n, okay, this is the n I'm talking about, this is my sample size n, okay. So let's be very clear, this is my n sample size, this is my sample size, this is sample size, okay, and I have k such samples, and I'll get k such means. And now central limit theorem says that if I plot these means, whatever is the distribution they are coming from, okay, whatever the distribution they are coming from, central limit theorem says that if I plot these means, they will follow a Gaussian distribution. So these means, okay, will follow a Gaussian distribution. The PDF of this mean will be a Gaussian. This is what central limit theorem says. I hope that is clear. And irrespective of whatever the distribution, underlying distribution it is, it doesn't matter whether these samples they are coming from a Bernoulli or a whatever unknown or some random sample, but the means, they will follow a Gaussian or a normal distribution as n becomes very large. So that is not the law of large numbers. So as n, for very large n tends to infinity, or for very large n, okay, for very large n, these all sample size, this is sample size n equal to 100, okay. For very large means for all practical purposes, what is large n? N should be at least greater than or equal to 30. Below this, n is considered small. So n should be greater than or equal to 30 to be considered large. If n is greater than 30 for each trial, okay, if I have at least 30 samples, then this will be considered as a large sample. And then if I plot these means, I will get a Gaussian distribution. This is what is central limit theorem. I hope this is clear, okay. And let's formally write it and understand some more things around this. So if central limit theorem is clear, so it talks only about the distribution of means. This is the distribution of means, the distribution of sample means, to be very clear, sample means for large n is greater than or equal to 30, and this is a Gaussian, okay. So this is the distribution of, this is the PDF. So these means, whatever we calculate, Okay, so there will be one central this will be a population mean, and then there will be, this will coincide with x bar will become mu equal to mu at the center, and then all these means that we calculate for each of these trials, they will be under this Gaussian. Okay, so now let's formally write it in mathematical terms also, and do some maths on that to understand what is the next topic, that is standard error. So let's write x1, x2 like that. Xn, as I mentioned earlier, are IID random variable. Okay, and so let me write that also. Okay, so these are random variables, and with a finite mean and variance. Finite mean mu and finite variance. Okay, let me write it, finite variance also. And so I have, for a sequence, so I have these random variables. So now for given this, the distribution of sample means will be Gaussian. And what will be the parameters of that Gaussian? So I'll just come to that. Okay, Gaussian, and this will be, generally I write it here, sigma square by n. So the mu will be the mu, as I mentioned here. This will be the mu, and the variance of this will be sigma square by n, not sigma square. Sigma is the data variance of the data, but the variance of this mean will be sigma square by n, and we'll prove that. And this is our standard error. This is called standard error, the standard square root of this. Okay, the standard deviation of this. And why the distribution will will be a Gaussian irrespective or regardless of the original population from which these samples are collected. These samples, population distribution, whatever is the distribution of these x1, x2, these sample means will follow a Gaussian. I hope that is clear. And now let's derive this. How is this variance? Sigma square by n. So again, as it is mentioned here, let's do. So x1, x2 and IID. So what will be the mean of this? So the mean will be expected value of xi, that will be equal to mu, that is the population mean, for very large number. That's what law of large number says. And then what will be my variance? My variance would be variance of xi. Xi is, what is xi? Xi is from here, x1, x2, xn are IID random variable, whatever, I don't know the distribution. So this I is coming, I will vary from 1 to n. This is I, and these are IID, independent and identically distributed, coming from the same kind of distribution. So this is the variance. Now, what will be my xn bar? The sample mean of all of this. So this will be 1 by n, sigma I equal to 1 to n xi. So this will be equal to 1 by n x1 plus x2 plus x3, so on till xn. This will be my sample mean. Okay, this is your population, this is your sample mean. And now I want to calculate. So this is coming, just watch carefully. This xi is denoting this data that we collected. This xn bar is the mean of this data. This is the sample mean of this data. Xn bar. This is the sample. This is what I am using. Okay, and now if I want to calculate, so what, and I am saying that this mean will follow a Gaussian with mu as the mean, and the variance will be this. So we know by law of large numbers that the sample mean will converge to mu as n grows large, that we know. And now the second part we have to calculate. By law of large numbers, the sample mean will converge to mu. That's what we saw here. law of large numbers. X bar converges to population mean. And now the second part is how the variance becomes sigma square by n. Let's do that. So how will we write variance of xn bar? This is your, not I, this is not xi bar. Variance of xi, this is equal to sigma. This is finite, less than infinity. Okay, this means that this is finite. Variance is sigma square. Sorry, sigma square. Okay, so we have, so variance of xi is sigma square. The underlying data, whatever is there, we can compute that, and that is finite. I want to compute the variance of the sample mean now. Okay, variance of the sample mean, what it will be. So for this, we have to calculate two things. This will be equal to, we will apply two known theorems. This will be equal to variance of, and then we'll put these things 1 by n, and this whole thing x1 plus x2 plus so on till xn. Okay, this is what it is. Xn bar is the average of all these, and I want to calculate the variance of this. So the two things we know already. We will, in the past, first thing is variance of x plus y is equal to variance of x plus variance of y, because covariance xy equal to 0. There's one more plus 2 times covariance of xy here, but this is equal to 0 because the assumption is IID, independent, and as soon as two variables are independent, the covariance becomes 0. We have seen that, we know that already, multiple times we have seen. So variance of x plus I is variance of x plus variance of y. What is the second thing? This is simple, you can do variance of some constant times c of x is equal to c square times variance of x. So this is a constant, and variance is all square terms. It is all the terms are squared. So this c, if you multiply with every term, so this c square will be multiplied with the variance. You can check it with a simple example and you will get this. So these are the two things. Now based on these two things, we'll recompute what this comes to be. So now this is equal to, now again we know that variance of, I want to compute this is equal to variance of 1 by n x1 plus x2 plus so on till xn. Okay, and now 1 by n is a constant, so this will come out, and what we know, c is c square, the constant times will come out, so this will be equal to 1 by n square times variance of x1 plus x2 plus so on till xn, and this will be equal to variance of x plus y is equal to variance of x plus variance of y. So this we can split it out separately. So it will be equal to variance of x1 plus variance of x2 plus so on till variance of xn. Right? This is n square. Okay, let's not miss the term. And we know that variance of any xi for the sample is equal to sigma square. Yes, we have put this for any I, just sigma square. So for each of the terms, we'll have sigma square plus so on till sigma square for each term. This will be n times for each of the term, n times for each of them. The variance is sigma square, same, because that is coming from the same sample. Next, so we can write this as 1 by n square into n times sigma square, because this is n times, this n square goes. Okay, so this will be equal to sigma square by n. So variance of sample mean is equal to sigma square by n, and that's what we proved here. This is the Gaussian. So the Gaussian final, the distribution of sample means, will be a Gaussian with mu and sigma square by n. Mu is the population mean, and this is the sigma square is the variance of the sample divided by n. N is the number of, this is the sample size. This is the sample size. I hope that is clear. Okay, and what is the next point? So we know that standard deviation is equal to square root of variance. Here, what is the variance of? So similarly, standard deviation of the sample mean. What will be the standard deviation of xn bar or sample mean? This will be equal to square root of sigma square by n. This will be equal to sigma by square root of n. So the variance of the data was sigma square. So standard deviation of the data will be the standard deviation of the data. Here only I'll write it. So standard deviation of the data would be square root of this. That will be sigma. But the standard deviation of the sample means is sigma by root n. And this in our context is called as standard error. This is also called a standard error. This is equal to sigma by root n. That is the standard deviation of not the data but the sample mean, whose distribution is mu and sigma square by n. Variance is this. So the standard deviation of the sample means is known as standard error, that is given by sigma by root n. I hope that is clear. So the standard deviation, I made it very clear. Again, let it be very clear. Standard deviation of the population is coming, that is sigma. Standard deviation of the data that we have, IID random variables, that is given by sigma. And then we calculated the sample means, and that sample mean follow a Gaussian because of Central Limit Theorem, whose mean is mu and whose variance is sigma square by n. And the standard error is given by, and the standard error is the standard deviation of the sample mean that is coming from the Gaussian here. I hope standard error is clear. Okay, and for making it more clear, so let's do a concrete example and then we'll move to standardize. Okay, let's standardize it also. Okay, standardize sample mean. So let's standardize. So what is standardizing any random variable? Standardize any random variable. Y is equal to, what do we do? Yi. So when we standardize this, what do? We do whatever is there, each value in yi, we subtract the population mean and divide it by the population standard deviation. This is also called mean centered standardization, means mean centered and variance scaled. So scaling factor is variance. Variance is standard deviation, that is square root of variance. So mean centered, I'm centering it towards the mean and I'm scaling it by the factor 1 by square root of variance, that is my standard deviation. This is my scaling factor is 1 by sigma. And for each of the data in the sample, each of the, there will be x1, x2 like that till xn, right, or y1, y2 till yn. So each of the sample, so instead of x I should write yi here to make it, so avoid the confusion. So this will be yi minus mu y, whatever is the population mean of that, and this will be sigma y. So this is mean centered. So if you take anything, right, this will make it, okay, the mean will become 0 and the variance will become 1 because of this. And if it is Gaussian, if it is coming from Gaussian, then this will become a Gaussian with mean 0 and variance as this will be mu and sigma. Mu is equal to, this is mu and this is sigma square because of the standardization. You can take any simple example, just play around. So let's say 1, 2, 3, this is sample, this is the mean, right? If I subtract the mean from each one, I'll just show you the mean centering part. Okay, So subtract from each of the data point. I have 3 samples. This will become, after mean centering, will become 1 minus 2 is minus 1, 2 minus 2 is 0, and 3 will become 1. Now what will be the mean, new mean of this? This will become 0. The mean of this will be 0. Similarly, you can calculate the standard deviation and then divide it by standard deviation. So automatically standard deviation will become 1. So this is what it does. It will move the mean to 0 and standard deviation to 1. It is called mean centered and variance scale. I hope this is clear. Standardize it. Why am I doing this? So just standardizing and showing you to give you one more information around this. So anything Z is the symbol for Gaussian. Okay, Gaussian here. Zn is equal to. So I'm standardizing my this thing. Sample mean. Standard. Okay. So I have standardized sample mean as xn bar in the sample mean minus mu, and what is the samples standard deviation? Variance of xn bar, square root of this is standard deviation of that is our standard error. This is also called standard error. This is equal to standard deviation of sample mean. I'm just repeating the point so that it becomes very, very clear and you don't forget this. So this is your 1 by n sigma I equal to 1 to n xi whatever by mu, and this will be sigma by root n because that was sigma square by n. And this, after standardizing, we say that d will tend to a normal distribution or a Gaussian distribution 0 to 1. And what does this d mean? So this d means, this d denotes convergence in distribution. Convergence, we discussed convergence in probability and in the previous video also. I'll put the link in the description. Convergence in distribution. So this is another type of convergence. Okay, so this d means after this is standardized, this will converge in distribution to normal or a Gaussian distribution with mean 0 and variance 1. And also this will, when will this converge? As n tends to infinity. Then we have more and more data sample, because then this will become 1. Both will become same and this variance will become same. Okay, 1. So we have discussed what is standard error. So I hope standard error is clear. Okay, and let me demonstrate again whatever I have mentioned earlier, what the central limit theorem say in a concrete way, whatever I have discussed earlier. I'll give you one more example so that it becomes very clear. What is sample and what are this? Okay, so the city example only. So let's collect the height of people in a city. Okay, and let's say the size of each sample is 100. So n is equal to 100 is my sample size, and I'm collecting height of people. And then let's repeat this collection 1000 times. Okay, so let's repeat this k is equal to 1000 times concretely. Okay, so I have one sample which has 100 heights of people, and I calculate the mean of this. Okay, so let's say that this is x1, which has x1, x2 like that till x100, and from this I get one x1 bar, x2 similarly this is 1 1 1 2 like that till 100 like that, and similarly for x2 this will be the sample. From this I get x2 bar, and like this I have xn, and again this I have 100 samples and I get xn bar. Okay, and now if I take, okay, if I have now k data points here, sorry, these are k. Okay, k, or this will be 1000, k is 1000 here, right? So n is equal to 100, this n is 100, and this k 1000 times. I am repeating the sampling 1000 times, 1 2 like this 1000 times. Now I get 1000 data points, and now I have plot these 1000 points. I will get a Gaussian. That's what I meant. This will be a Gaussian with some mean, and some mu will be mu, and then sigma square by n will be its variance. I hope that is clear. K is the number of repetitions, and we have to do this K number of times because only then we can plot it. Otherwise, if I just have one sample, what will I plot and what will I get? This is one data point. I will get some 1000 data points, only then I can plot this, right? So there will be some data points which I will get here. So for that I am doing it K number of times so that I can find out what is the plot like. Generally this will be histograms, one value, and from that we can take the tips and we plot it, and then we'll see that okay, this is a normal distribution. We plot it as histograms. This is clear now.